Good afternoon, all. Thank you for joining our today's webinar on length matching in high-speed buses. I'm Sairam, working as a team lead here at GSAS Metal Systems in Bangalore. And today's session is under recording. If anyone having any questions during the session, can put your questions in the chat. We'll discuss at the end of the presentation. And today's agenda is about we'll have the high-speed buses and its challenges. Then we'll look at the differential signals and why these also need length or time match. And before we go to the demo, we'll look at some of the techniques that are implemented in RTM in order to automate or semi-automate these tasks. From I think you can check from RTM YouTube channel where you can able to find a topic from BBC, which was speed edge. When we see a definition of a bus, when used in logic design, a bus is a set of data or address signals that go through to transmit a set of data or address where the data is stored in a memory. And we also see what typical technologies we see these buses in system like ME, PCI, CPU data, memory data, and memory addresses. In generally, systems that work synchronized with a clock or strobe signal. If we have a more detailed view, for example, an 8-bit data bus, we see the 8 datas on the clock. That means the system synchronized. Now the number of data lines can vary in CPU system today. We see 64-bit of data, whereas systems from early times was 8 data bits. Due to the complexity in routing 64 lines and manage their length and the fact that design gets smaller, we see a trend in moving towards serial systems rather than parallel systems. So how does it work? Now, if you see when a new data word is sent on a bus, the data is clocked into a register or a memory location. The clock must delay after the data word changes to ensure that all of the bits of data on the bus are valid when they are clocked. The faster the data is being transferred on the bus, the smaller the time is for the data bits to become valid and be clocked. For example, if the data is transferring at 1 Gbps per second, a data bit period is 1 nanosecond. That means there is only 1 nanosecond for the lifetime and part time of the signal and clocking in the data itself. What we see on the waveform is a definition of T surat, that means time required for data to be present before the clock. This is normally handled by microchip, but if we unintentionally delays the data by not paying the attention to the length match, we introduce extra time and reduce the margin of the timing. Now let us have a look at the differential pair signals. Differential pair signals are basic two signals complementary to each other, meaning that when one is logic high and other is logic low. This technique helps us with the noise introduction to the signal, makes the termination line more immune. The way the receiver detects a transition from 0 to 1 is the zero crossing of the two signals. As you see in the picture from micro clips, you can see these are lifetime content. This is how the single signal looks. Whereas different pair signals where both are of the same voltage levels but opposite polarity. At the receiver will observe the voltage differences to extract the right data. Because of the this opposite polarities, the noise will get eliminated. That is the these are different signals in the high speed signals. For example, USB 2.2 or HDMI signals. Due to this nature, the two signals must arrive at the receiver in the same time. The receiver might allow some difference called skew, and the skew can be found in the chip data sheet. If we again unintentionally route these signals with different length, we add some skew and thereby shortens the margin given by the chip tolerance itself. We see what the receiver will have to do within this picture from Science Direct. In the first column, we have a moderate skewed signal. In the rows, we see how the effect of signal versus a non-speed signal. The last row is a AC common mode that should be ideally be zero, but with a speed signal, we get more some AC spikes. Now, length and time matching in RTM. RTM supports both single-ended and differential pair length matching, and it's simply to use just activate the tool from within the PCB editor and drag the mouse until the gauze turns green. As you see here in the picture, where the length needs to be matched to minimum 70 mm and maximum 75 mm. The accordions added can be modified to fit your needs, making space for routing. And as you see, the length will be adjusted automatically. Same goes for differential pair signals, but here we have the positive and negative signals length in the text above the gauze. You can see here the gauze will show the positive and negative signals length. Now let us take a look how we can able to do it inside the Latin Visioner, how we can do this length matching of single ended signals and differential pair signals inside the RTM design. Now I will not designer for demonstration purpose. I have opened a project length match, and here we have the schematics. If you can see, we have got two channels, channel 1, channel 2, and we have differential per signal. By seeing these directives in Algebra, we can say easily these two are differential per signals. And for differential per signals, we need to add the directive. I mean, so net label to be added. That net label should be end with positive P or for positive net net name underscore P, and for the negative net the same name which is identified positive underscore N. We need to give. And in the latest version, we can able to define a suffix in the right options. Which suffix you want to tell the tool these are differential pairs, that is possible. But I recommend to go with this positive P and positive N so that anyone can easily understand by seeing these two naturally different pairs. And same way, we have got some design tools applied for this two differential pair signals. You can see by using directives where we have placed a blanket and we created a net class. We said it's a one class, and also we created a design rule for this differential pair. The length between these two nets, I think there is some spelling mistake. Let me correct. Between these two nets, it should not be more than 0.05 mm. That's what we have put in. And for the whole group of nets, we made as a class as channel 1, and we specified all the nets in this group should have a matching length of 0.2 mm. This one will give flexibility for adding the design rules to the Altium schematic editor itself, the same way how you can define in the PCB data. Now let us see how we can create these directives for the channel 2. Now I need to place the differential pair directives. You can access directives from here by right mouse click, you can see directives, or you can access the same from place directives. Okay, differential pair. Okay, now we place among these two, and yes, now we have the differential pairs been defined. Now we need to define net class differential pair rules for the this group of nets. Now let us have the same identical wise we need to do copy and paste here. Now we have filter over here. We'll go to filter and we just enable wire. Only wires will be selected. Then copy and paste over here. Now once it's done, I want to have these names to be pasted here. I can again do the same job. Others I can only enable net labels. I can just by holding shift I can able to drag it, the naming. Now I want this one, Control C. I want data 0 to be there. And later I just by holding shift I drag the net name. Okay. So now we have got the all the 7 data has been added. Now we want to add the design rule for this group of nets. Now let us place a blanket for this functional page, and let us place a one net class. Parameters that we need to add, and we place it as a net class, and here we are in net class. Net class. Here we have given the net class as one underscore clock. For this we do two underscore clock. Two underscore. Okay, and make it visible. Okay, now we need to add a design rule like channel 1, how we add for clock, the same length of 0.05 tolerance we have to add, matching length, the same parameter set we pick, and here also we use the same name like here, matching net length, or you can copy this instead of writing, you can also copy the net name and copy, I believe, I think this one. Yes, that's it. Now let us have this matching length and we just add a rule. This time we need to add a rule for matching length. And here we can able to pick an mm, and within decimal pair we want 0.02 mm thing in the decimal pair. Click OK. Okay. Now we can enable this one so to be see the net length rule. Okay. Like this, we can able to easily create the directives, and also we can easily define the net rules here. Okay. Now the same thing we can able to add it for the this whole group, but we'll just see how we can able to create the classes in the PCB. Now let us go to the PCB. There we will define the another net class for the leftovers. Okay, we just show you how we can create the same in the PCB as well. Now let us open the PCB. This is a PCB. We have the country has been placed. Now we need to get the design changes done inside the schematics to the PCB. For that, we need to go to design, import changes from the project. See what now design rules we have created in the schematic editor. We got the net class and a rule for the respective net class has been added to the PCB. Just click on execute changes and click close. Now we need to create a we have to take a look at the classes, what and all we have added in the schematic has been pushed or not, or if you want to create or modify any classes, you can able to access from design classes. Okay. Now see we have channel 1 class, they are the members of channel 1 class, and we have the clock class, these two are the members of the clock 2 class, and clock 1 class, and for the clock 2 class, they are the members. And we need to create a one more class for the channel 2. Just we need to add a class and the same name we just give the channel 2 underscore channel. And we want to make all these other members of this class. Click. Now, if you take a look at here, you can see we got the 4 classes have been created. Okay. Now, once the classes are created, we need to define the design rule for the net classes what you created, right? Like, see, we have created here point among the tolerance. The same way we have to create here because we are not done for the channel to class in the schematic. For that, we need to go to design rules. When you go to design rules, we need to define those under high speed. I just go to high speed under match length. See, these two are the design rules has been created in the schematics or pointing to the class what you have defined in the schematic. Now we need to add a new class. Okay, this we just create a new name. Okay, and just point the class that class in the way the object matches channel 2, and we need to give the tolerance as 0.2. Just apply and okay. Let us see the what is the 2. Yes, 0.2. Yes, correct. Now we have applied the design rule as well perfectly for this channel 2 class. We have got the all the net classes are in place. Now we are good to proceed further. Once you have the design rules done, now if you just zoom in, you can see the our official page by seeing this underscore p underscore and you can able to see. And if you go to the panels and if you go to the PCB and if you just go to the next and there here we have got the different pair edges. If you click on the all different pair editors, if you enable this, if you untick this, if you select this, it will show the all the this one. And if you select this, you can able to select the two pairs individually. Or you can also create the differential pairs from schematic PCB editor as well by using this option by defining the master network and giving that. Okay. Now let us see how we can route these two traces. Okay. Now let us route these differential pairs. Now I'm going to pick the differential pair routing from the syntax routing active bar. Just start routing it. Now let us start routing it. Okay. Now we have the differential pairs. If you want to, which is the this bend as well, as much as you can able to bend it. Now we got the uh, group of signals here. We have got the uh, channel one signals. We can able to do the you know multi-routing inside the by using this command. Just select the all the nets and then using multi-route to the all the places together. And now once you are done this, you can able to get this one also. Okay. Now, once we have this one, we need to see how the track length, whether they are in scope or out of scope. We need to access from the panels and PCB. If you go to panels PCB and a drop down next, you can see all the next. If you select, you can see the things which are out of scope, which are out of scope. Now we'll come with this different place. You can see we are told 0.05 is the tolerance which need to be allowed. But here, if you take a look at this particular thing, which is out of 0.05, a positive net, that means we are need to match the positive with respect to the negative because of the this bending because it has got more than compared to the positive. We just need to do the length matching. We'll just pick this signal as signal. Let's go to here, inductive and tuning. And when you press tab, you hear different routing patterns available. We have got accordion, trombone, sawtooth. Accordion is a recommended length matching option to have the continuous impedance maintained throughout the track. Whereas trombone and sawtooth are they don't maintain the proper impedance continuity. And these two are used where you have the space constraint in the length matching. But I prefer to have the accordion. You can have to control your steps and all from here. You just start doing it. Okay. Or if you can have more, if you can use 0.5, you get the single spike. See, we can able to control the amplitude and space from these options. We have different styles as well. Or by this space, we're able to control the different style. Okay. See now, as I told you, you have the gas coming when the length is being matched, will be done to the green. Okay. Now, if you take a look at this PCB, you can see both are matching. Still, why these are when both are matching? Why still these three are going in error? If you go to the channel one, we got the data 7 because of the longest path of this data 7. This has got the highest signal length, but rest all are not within the range of the tolerance what you set is 0.05. That's why all are flagged as a error here. That means we need to match all these net with reference to this particular data set, which tool automatically taken. The tool will take the length of the signal whose highest as a reference, and we need to match the signal length as per that. Okay. Now let us do the length matching for this differential pair next. Now we need to go for differential pair length tuning. And here you can have to control the this amplitude and other stuff here because 0.5 is being more which we may find difficulty in doing. We can control to 0.3 or something else based on requirement, and 0.1 is 0.2 or 0.2 let us keep and start doing the tuning. I think this is still we find difficulty and I have 0.5 only. You can see here the positive and negative, as you can see, it is showing the length. Okay, to be matched. If you want, you can have to push this one. You have to. You can also do like this. If you want, you can have to rotate it. Also to the do like this. Now you can see this PCB. See, both are having more than that. That's why it's showing an error. Let us. Beautiful. Oh, that is. I think I'm doing something not good. Just try to do editing, but it is going beyond our control. That's why I just stopped it. Okay. This is how we can see the now both are within the scope. Okay, now let us do for similar signal. Like this, you can do it for others. See how easy we can able to. Once you set the design rule, it is very easy and simple. You can able to do it. So now if you take a look at this PCB, you can see all of tolerance of 0.5. Okay, this is how you can able to easily do the length tuning of your differential pair signals as well as the your single line signals inside the multiplexer. Now we like to show you another useful thing where it will help you to do the automated routing for your signals, and which can help you to do the length matching as well. With the help of this active route, which will help you to do the length matching and automatically routing the tracks by using this active route. Basically, we have the group of net classes we created. As we have showed how to net class, we know I think how to define net classes. Once net class is defined, we have set the design rule inside the ultimate designer here for the latch length, what is the tolerance which should be allowed. We have set out automatically. Once you are set, we need to select the nets. We can see all the nets except the few are out of scope. All the nets. Now we need to use this PCB attribute for performing this auto router. Now we can choose the option called selected, and then if you want to gloss it, you can enable. And you need to choose a layer place you want to do the length tuning, and you need to specify the tool what is the thing just to follow, and automatically the rules will get applied. And here you can control the amplitude and the minimum space. We can just say the what is the minimum space and amplitude it requires. And then once we are done with this stuff, we can able to tell the tool to the active. Now, if you take a look at the PCB panel, we have the group of nets, and I believe one, two, there's two nets are out of the scope. This is a net where we just got them issue in terms of the matching. Maybe you can able to adjust this net further. I can able to again do the length tuning. Okay, this is all about the length matching in high-speed buses. Now